Part 3. This will be short because nobody cares about electronics, and I may start hacking myself to death. Okay, this is the circuit. Comes with a standard voltage divider. You can do anything in this section here to create the differential voltage. I first started out with a TL431, and that gave me like a 2.5 volt offset and gain in the thousands, and it just hopped around too much, because there was a very tight window between counting up and counting down, and that was just too erratic. So I went to a NPN transistor that I knew had a gain of only about 40. This is like Goldilocks, not too hot, not too cold. So it only had about a gain of 40, and that worked pretty good. But it did hunting because it would go too low and then too high. What I have is a series of diodes I showed you in the other video, sealed up in some heat shrink, and that's a temperature sensor, and also provides me an offset voltage of about 3 volts. So between 3 volts here, the transistor will have about 0.665. This voltage divider has to produce about 3.6 volts here before it starts to conduct. Transistors are a current device. It's not really a voltage. And no current will flow until you reach about that 3.6 volts. And once you get above that, this voltage really won't climb that much because any excess current just gets shunted down through these diodes. But anyways, at this point here, on this point here, we have the two resistors, a 2.7 and a 4.7K, and that turns the 12 volts into 7.6 volts approximately. And we have opto-isolators, and these are placed back to back. And so either one conducts or the other conducts, and they don't conduct until there's about a volt differential. And so there's really a 2 volt difference between when it goes up and down. So there'll be this dead point in between where the counting won't be updating all the time. So that makes it a lot nicer. And that's the reason I kind of chose this method. It's also because the electronics here is 3.3 volts in the PWM board. And there's two things, and that is it's very easy for you to make a mistake and send too much voltage into this, blow up the microprocessor. So it's nice to have this electrically isolated. And the other thing is that it allows electrical isolation for other voltages. So I may be putting this on 120 volts, and I want to have it electrically isolated. But, I mean, you could put an op amp here with an offset voltage and a little bit of gain. I ended up with a 2N2222 simply because I had a box of these, and the ones I tested had a gain of around 240, and that worked pretty well. 2N2222 is a switching transistor, so it is not a really good linear transistor, but all we need is just a little bit of gain, so this point here sits at about this voltage when nothing's happening. So you have enough current to bias these diodes. Some designs may take a pull-up resistor, attached to this point, so it always has this voltage, but you're always going to have this thing turning on to some point and passing current through it, so you'll get enough current through these diodes to sense the temperature. But it all comes out in the wash, it averages out together. So, but yeah, the two opto isolators can be anything. Now, you know, in design, it's always about how many parts you're going to use and the cost of those parts. So I used to work for a place that had a very high insertion fee. Basically, it was 43 cents per part to insert it. And that was back when 43 cents was real money. Uh, but I find that most of these things, you know, all take about the same number of parts. I'm just showing you that you can use about anything you want in electronics, you know, to do these functions. A little simpler method would be, again, you have this voltage divider creating a voltage. And in this one, I'd put a capacitor because the LM393 is a very fast comparator. And any noise coming down, I mean, remember, this is going out to an array. You're having those long wires, they're like a big antenna. So you want to filter out, you know, somebody coming by with a CB radio or something. You don't want it driving your system crazy. So, yeah, a little capacitor to filter out the noise. But again, these are open collectors, and you'll go right to the push buttons with these. It's just a pull down. And basically you have an upper voltage range and a lower voltage range. And you have a little pot in between here, and that will determine the differential. So you can, you know, adjust it up to, like, you know, if you have a scope or something like that to see where it trips from the upper to the lower voltage range. Just kind of very simple arrangement. This would be low cost, and I may use it in some design later on. But let's go down into the basement and see this thing running. Well, it's a gloomy day, and this is actually the output right on the collector of the transistor. And those two blue lines are kind of like the upper and lower limit. Boy, this is hard to see here. But there's a designation right here that says out, and down below it would be set. And when it's changing, the set will light up. Right now it's on out, and it really doesn't change at all. It's staying at the same. So we're at 57.9 volts. Here's the temperature sensor. I'm going to stick this in some warm water. And if we look, you can see the voltage slowly dropping. Now I can go ahead and take that and put it in some cold water to get back to normal. And we'll start seeing that climbing up again. And we're back up to about 58 volts. But this is just the noise from the capacitor bank, and right now it's just that 1.5 1500 microfarads. If I put the 6000 capacitor bank on it, you can see that the noise drops down a lot more. It'll still switch, but the large bank makes the thing cycle slower. So and most of you go cheap on capacitors, so yeah, this is what you get. And you can see, like I said, the two blue lines, once it goes above that or below that, it'll start changing numbers. But it's a cloudy day. This was, just when I started the video upstairs, 285, and now it's gone behind the trees and it's 126. But that's it.